Hello everyone, today we'll be covering part 2 of CIE A-Level Chemistry Atomic Structure, code 9701. Today we'll be talking about a further example of the electronic configurations and regarding the ionization energies and their trends. Okay, so last week, before that, I suggest that you check out last week's video if you haven't, where we talk about electronic configurations and the differences between electronic configurations and IGCSE and A levels. If you have, let's move on. So one thing that I realized that I forgot to cover last week is regarding electronic configurations is a special case. It's mainly asked in A2, like the second parts of A levels, where transition elements play a huge role, but in the AS it can be asked because it's within your syllabus. And the two special examples are chromium, chromium, it's chromium and copper. Okay, so why would they be special examples? How exactly are the special examples? Let's find out. So if you see the atomic number of chromium, which is also the number of electrons it has, is 24. And how would you write that in terms of electronic configuration? So it would be 1s2, 2s2, 2p6, 3s2, 3p6. So that's 18 electrons. 24 minus 18 is 6. And how would you normally write it? So 4s2 you fill first, and then 3d4, right? That's how it get. Or you can write it in a shorter form, argon, because 18 electrons in argon, 3d4 and 4s2, right? Now this is how I would normally write it, but writing it like this is wrong. And the reason is because, see, when you leave it like this, AR, okay, we assume that those are 18 electrons, and then 3d, first we draw 3d, like in terms of orbitals, 1, 2, 3, 4, and 5, and then 4s, right? So normally there's 1, 2, 3, and 4, and there's 2 electrons here. This is 3d, and this is 4s. So because this is half filled, for this to become more stable, like the most stable forms of an electron subshell is either half filled or full filled. So you can see that this is fully filled, like an electron pair is present, so this is fully stable, but this has only this has one missing, and it's not half filled. So for this to become more stable, you just bring one electron here to here, and what happens is, see, this becomes half filled, and this also becomes half filled. So it's a very stable electronic state, right? And the actual electronic configuration is AR 3d5 4s1. Okay, that's the actual electronic configuration of chromium. The same case is similar with copper. So if you check out the the atomic number of copper, you see that it's 29, right? So the electronic configuration of copper normally would be written as, like, if you're just following the basic principles, it'd be 3d9 4s2. And when you draw that out in terms of orbitals, it would be something like this, right? And 1 here. Now recall that I said that the two most stable states is when either the orbitals are half filled or fully filled, right? But over here you see that one's fully filled, but this one's half filled. So to make this at its most stable form, an electron goes from here to here, and so this is the actual electronic configuration of copper. This is the most stable form. So there's 3d, and this is 4s. That's an arrow, pardon the bad drawing. And this is full filled, this is half filled, whereas this is like an irregularity, and this is fully filled. So this is the more stable state. And therefore, the actual electronic configuration of copper is 3d10, 4s1, okay? And the reason why electrons can transition in between the 3d and 4s subshells is because they're, like, in terms of energy, they're very close together. So the electrons can transition in between these subshells, and that is why these elements are known as transition elements. Now that is something you'll cover more in depth in A2, so that is just the basic knowledge that you're required to have now. Okay, so now we'll move on to ionization energies. This is very often asked in the AS portion, and it comes usually for 10 to 15 marks, and it's very simple actually. So firstly, let's discuss what is ionization energy. Okay, ionization energy. So what is it? So I'll write an equation. Okay, for example, the ionization energy of magnesium. Okay, now what exactly does this mean? Okay, what happens in ionization energy is that an atom of an element in gaseous state is ionized to its positive form, like a positive ion, giving off an electron. So the ionization energy is the energy taken to do that, right? And this usually takes place in like a chamber where the atom is like bombarded with electrons, and it gives off an electron, like emits an electron, and it gets a positive charge, obviously, because it's losing an electron. It has a higher net positive charge, and that is exactly what ionization energy is. But when you're asked to define ionization energy, you're usually asked to define the first ionization energy. How exactly would you put it into words? Well, you take a look at this equation. Well, let's write it in a more standard form: x plus g plus e minus, and this is the first ionization energy because you see that this has a like no charge to a positive charge, so only one electron has been removed. So in general, what ionization energy is uh, the energy required to remove 1 mole of electron from an atom in its gaseous state. Okay, this is very important. And you can also write, if there's a 3-mark question, to turn it into 1 mole of an ion. This only applies if it's the first ionization energy, where it becomes from an atom to an ion, right? This atom and ion part. And that's pretty much it. So the first mark is the marks are distributed like this: energy required to remove 1 mole of electron from an atom in its gaseous state, right? And this can be awarded for the 3rd mark. Yeah. How would you change this so that it becomes the first ionization energy? Now, the way you do that is you just alter the definition a bit. Energy required to remove first electron from atom in gaseous state. Okay, and there's many ways to write ionization energy. Usually we just write IE is equal to x kj mole minus 1. And you'll realize that I'm pretty sure some of you recall the enthalpy changes in your IGCSE level. And when it's positive, energy is supplied, and when it's negative, energy is given out. Endothermic, exothermic, basically that. And the reason why this is positive is because energy is supplied, like energy is given or required to remove an electron, and like energy is not released. Yeah. And that is all regarding ionization energy, like the definition. Now let's take a look at a few ionization energy values. Okay. No, wait. Before that, whenever you're talking about ionization energy, in AS or your A levels as well, you have to like when they're normally going to ask you like reasons and trends, and like ask you to explain those trends, like the reasons for those trends. So whenever you comment on those type of questions, you have to give reference to, one, the nuclear charge. Okay, you have to say that whether it's changing or constant, but normally it's constant. Like, I've never seen an example where it changes. So you have to give reference to the nuclear charge. Secondly, you have to give reference to the distance between the outer shell electron, which is better known as the valence electron, and the nucleus. Okay, and the third thing that you have to give reference to is shielding effect. Now, most of you may be like, you. This is nothing. This is basic. So most of you may be confused regarding the second part and the third part. Like, how does the distance between the valence electron and nucleus affect the ionization energy, and what on earth is the shielding effect? So let's cover the second point in detail first. Okay. So the distance between electrons. So this is a positive. Okay. And let's assume the Bohr model for this. Okay. This is, yeah. So there's two electrons here and one electron here. Wait, let me just draw a larger cross so you can see it. So there's two electrons there and one electron here. Okay. So the distance between this and this, the further away the valence electron is from the nucleus, the weaker the nuclear attraction. This is a key term that you always have to give reference to. Okay, and it follows the equation, which is the Coulomb's one, Q by R square. So you can see that the force of attraction, so the electrostatic force, is inversely proportional to the radius, or like the distance between them, squared. Now this is something you learn in physics. You don't really have to know this equation in chemistry, but it's better to like help understand. So you see that each time the distance between the valence electron and the positive nucleus increases, the force of attraction between them, the electrostatic force of attraction, decreases by the square of that amount. So that is something you have to give reference to. And now the third thing, just give me a minute, I have to remove this as well. Just remove that. The third thing you have to give reference to is shielding effect, right? So there's the positively charged nucleus. This is the first shell, and this is the second shell. Okay. So you see that what this shielding effect basically is. So before that, you have to understand the basic principle that electrons are negatively charged, and therefore they repel each other. Okay. Now the reason why, like, the shielding effect basically means that you see the electrons on the outer shell, the outer principal shell. These will be subject to a shielding effect because of the inner electrons, like the electrons present in the inner principal shell. Now the reason why is because the electrons are negatively charged, so they're repelled. So this electron, while it has an attraction towards the nucleus, it will be repelled by the electrons in this, and these are constantly orbiting. So the outer electrons are repelled by this this inner shell of electrons. That's basically what the shielding effect is. Now to recap, the three things that you need to refer to when you're talking or giving explanations regarding shielding effect, sorry, giving explanation regarding the ionization energies, is firstly the nuclear charge, secondly the distance of the valence electrons from the nucleus, and thirdly the shielding effect. Now let's take a look at a few of the, I have like a list of values. Let's take a look at a few ionization energy values. Okay. Okay, this is exactly as your data booklet, this is exactly what's there in your data booklet. So as you can see, for every element, there's a successive increase in the ionization energy. Like for nitrogen, first ionization energy is this, second is higher, third is higher, fourth is even higher. So there's a successive increase. And normally, there's some times where you're asked to give reasons as to why there's an increase. And recall what I said earlier, that you have to give reference to those three things. So if I asked you why across the period the ionization energy decreases. So how would you answer this? Think about it for a few seconds. You feel free to pause the video and then answer and then check with what I say. So remember that I told you to give reference to three things: the nuclear charge, the distance of valence electrons from the nucleus, so radius, and the shielding effect, right? So why does it increase across the period? Sorry, not increase across the period, increase like successively. Okay, I'll get onto the period later on, okay? The reason why this happens is because, assuming that it's nitrogen, so there's how many electrons? Nitrogen is 7, right? So, and 7, 1s2, 2s2, 2p, so it's 4, 4, 3, so 2p3, right? So when you remove the first electron, there's 2 left, right? So the nuclear charge increases, whereas the radius or the distance of the outer electron with the nucleus is reasonably the same, the constant. And the shielding effect is also the same because it's the same shell, like the shell isn't decreasing. So because there's an increase in nuclear charge and the radius and the shielding effect remains the same, the nuclear attraction is stronger, and therefore the ionization energy increases successively for in case of every element. Okay, I hope that makes sense. Now let's get on to the trends, like across the period, down the group, and a few special cases. Okay, so firstly, across the period. Now, how do you think the ionization energies, the first ionization energies, okay, the first ionization energies, varies across the period? Uh, you can pause the video and think about it for a bit. Okay, so regarding the first ionization energy across the period, the actual answer is that in general, because there are a few special cases which we'll get onto later, so in general, it increases across the period. Now, why is that? And that is because across the period, there is an increase in nuclear charge. Okay, and electrons are added to the same shell, so the distance between the nucleus and the distance between the nucleus and the outer shell electrons is reasonably constant, and because electrons are added to the same shell, okay, electrons are added to the same shell, the shielding effect is also reasonably constant, okay, and because of that, there's a stronger nuclear, there's an increasing nuclear attraction, and therefore increased ionization energy. More energy is needed to ionize the element, right? So let's say nitrogen, not nitrogen, oxygen. What is a proper example? So across the third period, so let's say there's magnesium and sodium, right? Magnesium is across the period, like more to the right of the period than sodium, right? So by that general trend, magnesium should have a higher first ionization energy than sodium. Is that the case? Yes. 494 for sodium and 736 for magnesium. I hope that makes sense. Now, we did across the period. Now let's think about down the group, okay? This is even easier if you understood the previous. I'll give you can feel free to pause the video and think about it for a while. Now regarding down the group, if you go down the group, you'll realize that yes, nuclear charge increases, but so does the distance between the nucleus and the outer shell electron. And because the number of shells are increasing, there is an increase in shielding effect. Now, the effect of these two outweigh the effect of this, and therefore nuclear attraction is weaker, therefore the ionization energy, decreases down the group. I hope that makes sense. So let's take an example directly from the periodic table. Sodium and potassium. Potassium is more down the group than sodium. So by the general trend, it should have a lower ionization energy. Let's take a look. Potassium is 418 and sodium is 494. So it follows the trend. I hope that makes sense. Now, there are a few special cases, okay? So remember before I said that across the period, there's like I mentioned, just give me a minute. Okay. So remember before I said that there are a few special cases. I like highlighted the term general, like across the period. Okay. Oh, apologies. Across period. Okay. So the reason why I said it was general is because there is a few exceptions, and those exceptions are that there are two exceptions. Okay. The first exception being between magnesium and aluminium. Okay. Or any two, like any two. It can even be between wait, just let me go here. Beryllium and boron can be between these two, or it's mainly between magnesium and aluminium, okay? And let's get on to why that's the case, okay? So magnesium has an atomic number of, I believe, 12, and aluminium has an atomic number of 13, okay? So it'll be 1s2, 2s2, 2p, 6, right, and 3s2. Whereas aluminium is 1s2, 2s2, 2p6, 3s2, 3p1. So following the trend across the period, aluminium should have generally a higher ionization energy. But is that the case? Let's find out. So magnesium is 436. Is aluminium given here? I hope it is. Okay, yeah, aluminium is right beneath. So as you can see, aluminium has a lower ionization energy. Now, why is that the case? The reason is because of the orbitals. Is because of the energy levels of the orbitals. So you see that the outer electron of magnesium is present in the 3s2 orbital, whereas for aluminium it's present in the 3p1 orbital, okay, or the subshell, as you may call it. And recall that 3p is in a higher energy level than 3s, right? So despite the nuclear charge increasing, there is a slight increase in a distance between the outer electron and the nucleus. And because of that, there's also an increase in shielding effect. And because of that because of these two increases, this outweighs the effect of the increasing nuclear charge, and therefore the ionization energy of aluminium is lower than Mg, the first ionization energy at least. And the way you'd write this is that despite the nuclear charge increasing, the outer electron or the valence electron of aluminium is in 3p orbital or substellar orbital, which has more energy than 3s orbital. And you can also add in here that the outer, like the valence electron of magnesium is in 3s orbital, and therefore there's an increase in distance between nucleus and outer shell electron, and there's an increase in shielding effect, therefore weaker nuclear attraction. So what happens because of the weaker nuclear attraction? Lower first ionization energy. Okay, that is the reason. Now that's the first exception. What is the second exception? And no, the two exceptions are not between boron, beryllium, magnesium, aluminium. Those are not two exceptions. That's just one trend. The second exception is between. Let's slide in here. So the second exception is between Nitrogen and oxygen, phosphorus and sulfur. Okay. I wanted to use nitrogen and oxygen in like an example before, but then I realized that it follows the same trend as phosphorus and sulfur. So anyway, they normally do it across the third period, so we'll just talk about phosphorus and sulfur, okay? Just give me a minute. Let's slide onto this side. So between phosphorus and sulfur, their atomic numbers are 15 and 16, if I'm not mistaken. So when you draw it, 1s2, 2s2, 2p6, 3s2, 3p3, right? And for sulfur, it's 1s2, 2s2, 2p6, 3s2, 3p4. So again, by the trend, sulfur must have a higher ionization energy, but it doesn't. As you can see, sulfur has a lower ionization energy than phosphorus. Now, why is that? Now, you can't really tell much. Like, maybe you can once you're more experienced, but if you're a beginner, you can't really tell much from the information given in the electronic configuration. So you have to draw the orbitals, and for what's of significance is the 3p orbital, okay? This is of phosphorus and this is of sulfur, and this is the 3p orbital, okay? These are 3p orbitals. Now for for phosphorus, it's half filled, whereas for sulfur, one of them has a pair of electrons. So this one is more stable. Recall that it was said that at the beginning of the lesson. This one is more stable, right? And this one, because it has a pair of electrons in one of the orbitals, these two electrons, because they're negatively charged, they experience something called electron spin pair repulsion. And this repulsion decreases decreases the amount of energy required to remove that second electron, remove that first electron from an atom of sulfur. So when you're asked as to why this trend exists, like why it's like this, it'll be something like this. This is how you have to comment. What you have to say is basically between phosphorus and sulfur, the valence electron of sulfur. Okay, you can write for both. Of phosphorus is in 3p. Sorry, the valence. Okay, no. That valence electrons of both phosphorus and sulfur are in 3p subshell, but phosphorus has half-filled 3p subshell, whereas sulfur has pair of electrons in, okay, wait, let me just slide down, in one of its 3p orbitals. Therefore, electron spin pair repulsion, and this term is very important, so lower first ionization energy. Okay, over here you could also comment on like the increasing nuclear charge and all that, but it's not really that important. All you have to focus on is this electron spin pair repulsion. This is what they look for mainly. Okay, I hope you understood. If you do have any doubts, please leave them in the comment section below. That is all, and the next lesson we'll be starting with is chemical bonding, and hopefully we'll begin that soon.